This is a short presentation on the application of vector addition to a Fibonacci-like sequence using real vectors at a constant angle. And then I examine the ratios of two of the consecutive vector magnitudes in this sequence at the convergence to the limit. This sequence is implemented as the Fibonacci sequence of vectors, where the next vector in the sequence is the vector addition of the last two vectors in this sequence with a constant angle between the vectors. The ratio of any two consecutive vector magnitudes approaches a limit as the number of the sequences get larger. These sequences are calculated on a range of angles from 0 to 120 degrees. The angles greater than 120 degrees are also investigated later in the document. This analysis only considers the positive square roots. Here is the vector analysis of the vectors, and it's basically just using the law of cosines and then looking at the ratio of Vn plus 1 over Vn, and those are the magnitudes. And this is all at a constant angle. Now the first one, I start at 1, V1 is equal to 1, and V2 is equal to 1. And it is at some angle theta. This spreadsheet below shows the calculations of the sequence at different angles between the vectors. As you can see, this is taken at 0 angle, 10, 20, 30, 40, all up to 120. And then the first two are given, 1, 1 in each of them. And then as you can see, this particular sequence is the Fibonacci sequence. At 10 degrees, you can see it deviates from that sequence, and it is increasing like the Fibonacci sequence. And as you approach 120 degrees, the sequence does not increase, and it's just 1 all the way, just because of the mathematics implied. This is an example of the equation I used from the previous page applied in Excel. In this table, I take the ratios of each of the numbers in the sequence at each of the degrees that we calculated in the earlier page and look at those ratios. And of course, at 0 degrees, it approaches the golden ratio, because vector addition at 0 degrees is basically the same in terms of their magnitudes as the algebraic addition. But as you increase the angle between them, as you can see, it does approach some limit as you go up, and you can see the ratios here at the different angles are decreasing from 1.618, the golden ratio, down to 1 at 120 degrees. I took the ratios and applied them as a function of the angle between them, looked at the ratios, and then fit a curve to those ratios. And it's interesting that it fits a third order polynomial almost basically exactly. The first chart is a plot of the ratios of the Fibonacci numbers as they increase. We're looking at a fit for that, but it's no big deal in terms of its fit. But you can see it does approach a limit as the numbers increase, the sequence numbers increase. What I did here was I just took every other ratio calculated in the sequence. And as you can see, and you'll see later on too why I did this, it's just a different way of looking at this. you can see if you take every other one, it approaches from decreasing, and then this one approaches from beneath, which is increasing to the limit. It's just a different way of looking at it, but you'll see why I did that in a minute. In this next part of the discussion, I'm looking at angles above 120 degrees up to 180. And there's some interesting relationships that are discovered here. The magnitude of the vector addition sequence approaches 0 as the number of iterations increase. So the numbers are decreasing. If you look at it graphically, it sort of makes sense. And the ratios of two consecutive vectors has a lesser rate of convergence as the angles increase above 120 and has multiple limits sometimes. Charts illustrate this in the next page. Here's the tables of numbers. It shows how the vector sequences reduces in magnitude. From 125, I went up to 180. In this table, I'm showing the ratios, and I used Excel to show the magnitudes of the background color of each cell. You can see how the magnitudes vary by color, and then we'll look at it numerically. But do notice that the values are decreasing. The ratios are decreasing. Here I'm illustrating the ratios at an angle of 130 degrees. And you can see if I take every other one in the sequence column you can see it approaches a limit from the bottom as well as the top. And in this particular case, that limit is the 0.8986991. Here's the ratios at 140 degrees. Again, the limit is a little bit lower. It takes a little bit longer in terms of the number of sequences for it to approach the limit. But again, I took every other one, and you can see it approaches from the bottom and the top. Now at 145 degrees, you see there's two limits, and they are not approaching each other. At 150 degrees between the vectors, again, two limits, 1.229 and 0.50275. At 155 degrees, I have four different curves going in, but you can see that as you go on to more numbers in the sequence, they do approach a limit. Again, from below and above on each of them. 160 degrees, you can see I've got 2, 4, 5, 6, 7, 8. They don't look like they're converging. I know the numbers are getting a little bit small here, so it could be due to precision of the computer, but it does look like there's 8 different limits here. Now, if I go up to 170 degrees, here's all the data on this chart, and it looks fairly random. I don't see any converging to limits. I'm not sure if it's due to the precision or the nature of it at 170 degrees. 175 degrees, again, I don't see any real patterns there. Again, the numbers are getting small. If we look back, you look at these numbers down in here, 170, 175. these numbers are starting to get pretty small. So whether the accuracy of them, or maybe there is a pattern in there, but I was not able to see it. Okay, in conclusion, I think the biggest interesting point here is that the ratios fit a third order polynomial. They decrease and they fit a third order polynomial up to 120 degrees. Once you get up above 120 degrees, they don't fit that nice curve. So something unique about the 120 degrees. And then to repeat, as the angles get greater than 120 degrees, the magnitudes of the vector addition sequence approaches 0 as the number of iterations increase. Whereas below 120 degrees, the magnitudes increase. Number 3, as the angle is greater than 120 degrees, the ratio of two consecutive vectors starts to decrease the rate of convergence as the angle increases, with some converging to one limit from two directions and others having multiple limits. And then the last point I stated already. Hope you enjoyed the discussion. If you have any comments, please leave them on the YouTube channel. Thank you.